All right, good morning. Buenos dias. And I want to welcome you to Plenary number 6, which is realizing Mars sample return through human and robotic collaboration. My name is Cheryl Reed, and I'm from the Johns Hopkins University Applied Physics Lab. I'm the Civil Space Program Development Manager there, known as APL. APL is Dr. Jeff Johnson is the current chair for the Mars Exploration, NASA's Science Mission Director at Mars Exploration Planning and Assessment Group. I have the privilege to have 4 very distinguished panelists here with us today, and I'd like to give a brief introduction of those panelists. Formerly, we had Dr. Ellen Stofan, NASA's chief scientist, to be with us, and she unexpectedly had to go back to Washington yesterday. It's our great pleasure that Dr. Jonathan Lenine is filling in for Ellen. He's a professor of the physical sciences at Cornell University and the director of the Cornell Center for Astrophysics and Planetary Science. Jonathan's a member of the National Academy of Sciences, does many studies, and most recently co-chaired the Pathways to Exploration study on human spaceflight for the National Academy. We also have Dr. David Parker, who is the Director of Human Spaceflight and Robotic Exploration from the European Space Agency. Mr. Parker was appointed to the director position in the April of 2016, and prior to this appointment, he served as the Chief Executive for the United Kingdom Space Agency, where he was responsible for overall space agency leadership. We also have Mr. Charles Wetzel, who's the manager of the Mars Program Formulation Office at NASA JPL. Mr. Wetzel currently works in NASA's Mars Exploration Program as the manager of the Program Formulation Office and has worked for over 25 years in Mars-related position, including chief engineer for the Curiosity rover. And we have Dr. Masaki Fujimoto, who is the director of the Department of Solar System Science from JAXA. He's served as the director of Solar System Science within JAXA's Institute of Space and Astronautical Science since 2010. And Dr. Fujimoto is also the Bippi-Colombo MMO project scientist and the lead for the Martian Moons Explorer Study team. This plenary is sponsored by the IAF Technical Committee, the Space Exploration Committee, and we believe that it's our charter to work collaboratively with both the robotic and the human communities. And we do this through the committee work of agencies, academia, and international consortiums like the ISEG, the International Space Exploration Coordination Group. We see Mars as a joint horizon goal globally across many countries. There are new countries that are joining that pursuit all the time, and pathways for new entrants of new countries to also do so. We see Mars sample return as an important contribution to this pursuit, where nations can come together, exchange scientific, strategic knowledge, technology, capabilities, joint missions, and operational pursuits. These are the types of topics we'll be talking about today, and we'll explore the roles of the individual countries within this global endeavor. So the format for today's plenary is that we will have a brief talk from each of our distinguished panelists. We will then have questions by the moderator. We will also have an opportunity to take a few questions from the audience. We have some volunteers that will be carrying around paper for those questions, and those questions will go into Ms. Kathy Larini here, and she will in turn give them to me, and then we'll have a short summary. So it should be a wonderful hour of discussion, and we do indeed hope you enjoy our discussion. And with that, we will start off with Dr. Lenine from Cornell University.
Thank you, Cheryl. Good morning, everyone. Let me start by letting you know that I am not a NASA employee, and so what I will be saying comes from my own scientific background and views working in planetary science for the last 30, 35 years. However, I will use Dr. Stofan's slides, and for those friends of mine in the agency, NASA, you can be assured that our views are really quite concordant with each other. The most profound question that we can ask as a human species is whether we are alone in the cosmos and where we came from. The answer to that question is going to come in large part from the exploration of the solar system. It's going to come from looking at the other planets and moons of our solar system to understand, number one, whether life had a second separate origin somewhere else in the solar system, and also what the earliest history of the Earth was and how it became habitable and why it has sustained its habitability over 4.5 billion years. Complex life required 4 billion of those 4.5 billion years to arise. And of course, we came on the scene in a very, very short time compared to geologic time. So the places we would go look for life in our solar system are shown back here. They are Saturn's moon Titan, Jupiter's moon Europa, Saturn's moon Enceladus, and Mars. And of these, Mars holds a very special position. It is uniquely accessible. We have explored Mars to a greater extent than any of these other bodies. And as a terrestrial planet, as a rocky planet, with a composition not very different from that of the Earth, we can compare the early history of Mars to the early history of the Earth. So if we think about our own moon for the moment, its geologic history ended within the first billion years of its history, 500 million to 1 billion years of its history. And so the moon gives us a record of the first 500 million years of the history of our own planet Earth, which we don't have on the Earth itself. Mars has continued to evolve geologically, but its habitability, based on our knowledge from spacecraft missions, essentially ended 3.5 billion years ago. In that first 500 million to 1 billion years of Mars history, there was, based on images and geochemical data from orbiters and from the surface, ample liquid water that flowed across the surface in networks, valley networks, and flood channels like what you see here. And standing liquid water may have existed on the surface as well. Interestingly, this gives us the opportunity to see the entire habitable history of a terrestrial planet preserved for us today. The Earth's habitable history is still with us. It's not over. And the other interesting thing that this provides us is that if life began on Mars, and it may well have begun first on Mars and was transported to the Earth by impacts, then because Mars's habitability, its ability to sustain life, ended so early, that life, even if it exists today, is restricted to very small pockets under the surface, deep in the crust, doesn't have access to energy sources like the sun and therefore photosynthesis, and so undoubtedly has not evolved or has not evolved the way life on Earth has evolved. So if we can find organisms, either extinct, remnant fossils of organisms, chemical, geological, physical records, or eventually find life itself, we have a unique opportunity to understand that first 500 million to 1 billion years of the history of life on a terrestrial planet. Again, something that's lost to us on the Earth because all of life, no matter how primitive, has co-evolved over 4 billion years. And therefore, although we have the genetic record, the genomic record of that early history, we don't really have the metabolic and physiological record, which we may have on Mars. At the same time, Mars today is cold, dry, desiccated, surface is sterile. It's bombarded by ultraviolet light and by cosmic rays. The atmosphere reacts with the surface to produce a strongly oxidized layer. And so exploring the surface of Mars to find its history is difficult. It's difficult from orbit, it's difficult from the ground. And yet, a remarkable series of successes beginning at the start of this century, the start of this millennium, extending to today by robotic spacecraft from the United States, from Europe, European Space Agency and its national partners, and from the Indian Space Agency, have provided us with a very detailed record of that early history, both from orbit and from the ground, so that we can be very, very sure that Mars had standing liquid water in various places on the surface. We can be very sure that that water had time enough to interact with organic molecules that were present. It had enough time to build a sedimentary record in some places on the surface. And so the next question is, did life arise? Where did it arise? How long did it have to evolve? And where did it end up as Mars dried up and became uninhabitable? A lot of that story has begun to be sketched out by very sophisticated robotic spacecraft on the surface of Mars, in situ studies. And yet, a surprisingly large number of the questions that we would ask today are not going to be answered in detail or definitively by in situ or orbital investigations. It will require returning samples from Mars. Returning samples from Mars to the Earth allows those samples to be subjected to very, very powerful laboratory techniques that exist today in terrestrial facilities that cannot be replicated on Mars at present, and even more sophisticated facilities that will exist in the future. Those samples will be there to be studied by the next generation of instruments. Now, one can argue that we can develop very sophisticated instruments, even more sophisticated, send them back to Mars and so forth. But eventually, you get to the point where the cost of replicating terrestrial laboratories on robotic spacecraft on the surface of Mars will actually exceed the cost of returning samples. And for many kinds of investigations, we're at that point today. So let me give you two quick examples. The Martian meteorite ALH 84001, a meteorite that was blasted off the Mars surface, found its way to the Earth and has been studied in terrestrial laboratories. Much of the detailed study of the texture and morphology in that meteorite is done at a spatial scale that today cannot be done from robotic spacecraft and will be very, very difficult to do on robotic spacecraft for the foreseeable future. The detailed isotopic analysis of this meteorite, which established that much of the organic material was actually terrestrial contaminant, but some of it was from Mars, again requires facilities that cannot be brought to Mars, and for the foreseeable future cannot be brought there. The second example I want to give is radioisotopic dating. Although there are ways to do remote isotopic dating from in situ missions to get very precise dates and therefore to put together a history of the Martian crust and mantle material that may be there, requires bringing samples back to a terrestrial laboratory and doing radioisotopic dating in that laboratory. The types of analyses, the amounts of material, the levels of cleanliness and avoidance of contamination are all things that require terrestrial laboratories and experts who do this sort of thing for a living in those laboratories. The ability to accurately isotopically date meteorites and lunar material, lunar samples brought back from the moon by Apollo astronauts and by the Russian robotic spacecraft, has revolutionized our understanding of the solar system. It has given us an absolute chronology for the first 500 million years of the history of the solar system. Doing the same thing for documented samples from the surface of Mars will revolutionize our understanding of the early history of Mars, the first billion years of terrestrial evolution, and the whole chronology of when and how Mars went from being habitable to uninhabitable at its surface. Now, finally, bringing samples back will allow scientists to analyze in detail the composition of both the fine material and the whole rock material and get a complete assay that will allow us to understand all of the material, including potentially hazardous material for future astronauts that's present in the Martian crust. The Martian crust is chemically very active. It's interacted with the atmosphere. It's essential to understand what is there and what future astronauts will be in contact with. And much of that will be done and will have to be done by not only in situ, but by return samples. So I want to emphasize again, what robotic spacecraft are doing is remarkable today. Curiosity has begun the stratigraphic analysis of Mount Sharp, and we are going to discover, as in this image, an incredibly intricate geologic history. And as we do that, we're going to want to do analyses that have to be done from the Earth. And as we think about this remarkable world that astronauts will go visit, we'll want to understand the environment of that world to make sure that those astronauts are safe in their long-term exploration of the Martian surface. And so, as we plan a technological infrastructure for bringing humans to Mars, having them explore for long periods, and even keeping them there, we will have to embed within that technological infrastructure a logical and doable program of in situ and sample return missions. And the payoff of that is that we will not only be exploring an extraordinarily interesting world, but we'll understand in a much more profound way than we do today how our own planet became habitable, where we came from, and whether we are a unique or, in some respects, a common outcome of cosmic evolution. Thank you.
Thank you very much, Jonathan. Next presentation, please. I'd like to bring to the podium Mr. Charles Wetzel, from NASA JPL, who will tell us a bit about the architectural studies that have been going on with human-assisted Mars sample return. Next
Good morning.
presentation.
Yes. Slides. Thank you. Good morning. Dr. Lenine's just done an outstanding job talking about the importance of the science that can be done. I can't really add anything to that. So what I would also like to remind people, I was going to do this on behalf of some of the young and new faces that I've been seeing around the conference all week, that this has been an item that's been at the top of the planetary science to-do list for a long time. There have been a number of prior studies. Those of you that have been around for a number of years are well aware of that. What I wanted to emphasize more this morning is our recent thinking that's changed over the last couple of years in terms of looking at sample return as something that can be accomplished in the context of a partnership, and a partnership in several different capacities. A partnership between the multiple different missions that it will take to acquire the samples, bring the samples back, and transport them across the solar system back here. A partnership across different multiple agencies and between the agencies and industry, and a partnership between human and robotic exploration. And we're going to go into that in more detail this morning to explain what we mean by that and some of the ways that partnership could play out. Having been studied for so long, one of the benefits we have in taking up the question of sample return architectures today is to look back at all of the prior studies and see patterns that emerge there and the understanding that we have of how the mission must be implemented. All of the prior approaches, they may differ in their implementation or different in specific technology choices, but they all consist of a set of fundamental building block capabilities. Different architectures group those building blocks into different groups to form different mission concepts for how to approach it, but the set of fundamental capabilities that are shown up here all are the essential things that have to be done to make this thing happen. Rather than to spend time to go into these in any depth and read through them one by one, I simply want to make a couple of observations about this set of capabilities. Although it's a long list, the first point I want to make is that each of them by itself is a tractable problem. Each of them is a well-defined problem that's understood, and a good team with the right engineers and the right mandate and the right funding commitment could go off and tackle those problems and bring these systems back together. And that's an important message or an important way to think about the overall set of capabilities that are needed to do this. The second important observation is if you look at all of those steps along the way that have to be done to get there, to acquire samples and bring them back to the Earth, it performs a perfect opportunity to conduct a round-trip trailblazer of all of the mission phases, the environments that we're going to have to master and we're going to have to understand in order to take humans from the surface of the Earth to Mars and to return them safely. And that's an area where this opportunity for collaboration and partnership between human exploration and robotic exploration really can come into its own. In terms of the prior studies, I want to take the opportunity to highlight a couple of those that have been done in the past, in the more distant past, that were sponsored by the International Mars Exploration Working Group. This is kind of a self-selected group of agencies that have interest in the exploration of Mars and have provided resources and come together to consider these problems over the years. Two specific studies that were both under the flag of the International Mars Architecture for Return of Samples, the IMARS studies, were conducted in 2008 and in 2015. Although they came up with different ways of parsing the problem and breaking these into different mission concepts, they both came back and used this same set of building blocks. The other key finding that that group had was that these technical building blocks, the technical capabilities that are shown up here, also form a good basis to talk about those partnership opportunities. Each of these self-contained chunks of functionality are also good building blocks that individual agencies and individual industry teams can talk about their interests and their capabilities and their ability to bring those things together. The last box on here, Safe Earth Return, is a box I would like to go into in a little bit more depth and highlight a couple of studies, two different studies that have happened over the last 2 years, one of which really brings home the opportunities that exist for a human-assisted sample return, or a role that humans could play in that. As with a number of different organizations in the aerospace community, we've become enamored of the maturity of the solar electric propulsion technology that's come online in the last 5 to 10 years. And that's opened up a different way of thinking about that safe return back to Earth. With solar electric propulsion, we've got opportunities, a lot more Delta V to work with, opportunity to fold in other mission objectives like site reconnaissance or exploring resources and things like that. So the idea that an orbiter that started the return leg of capturing samples on orbit that had been lofted there by a Mars ascent vehicle could transfer those to another vehicle almost anywhere where it would make sense to be convenient. So the study that's shown under the human-assisted sample return was sponsored a couple of years ago to look at opportunities to hand off the samples between a robotic mission and some of the crew capabilities that are coming online. At the time, we looked at that in the context of infrastructure we expect to be in place in cislunar space, and a couple of advantages were identified to that approach. One of them has to do with this cleanliness and containment that we take very seriously. It's a two-way seal that we have to worry about, both protecting the samples from contamination of Earth sources, as Dr. Lenin alluded to, but more importantly, protecting Earth from the Mars material itself. We want to treat this very carefully, treat it very safely, and make sure that it's maintained under containment until it's safe in those laboratories on the Earth. And so having an opportunity for the crew to provide an inspection of that sealing process, repeat levels of sealing if necessary. Those are capabilities that having crew involved could easily bring to bear. And a second important capability there that was the sense that bringing the samples back on a crew return vehicle with an established track record could also go a long way towards assuaging people's fears or concerns about the safety of the overall approach. The second approach we've spent time thinking about in the last couple of years is a variation on that same theme, looking at handoff between multiple orbits. In this case, the idea is that a first orbiter would rendezvous with the samples and provide that initial containment, and then be able to hand them off to a second robotic mission. In that case, the first mission would be free to continue on and do other things in Mars orbit. If it had been scouting for future human landing sites or doing other resource prospecting, then it could remain in place and provide those functions or relay functions at Mars, while a courier spacecraft would bring those samples from Mars orbit back to Earth. And that's a study that's been led by our colleagues at ESA over the course of this last summer that we jointly participated in. The thoughts I'd like to leave you with, right, are that we really feel like the accomplishment of the sample return as an overall enterprise should be taken in the context of a cooperative set of missions. That's the more cost-effective way of doing it. It allows different pieces to be approached by different organizations, spreads those costs out over time, and that's a way of making the mission achievable and spreading the objectives across different organizations that can take responsibility for different pieces. We also feel that the capabilities to accomplish all of the things that are needed to do sample return are understood. They're within our grasp. We just need to have the resolve to get a plan together and focus on those to go and do them. As I mentioned before, we think this provides an opportunity for multiple different agencies and industry teams to trailblaze this exciting endeavor, to do the things that are serving as that round-trip trailblazer for human exploration in all of the environments and all of the mission phases that are needed. As Dr. Lindeen alluded to, once the samples are back here on the Earth, an opportunity for scientists from all over the planet to come together, participate in that discovery, and conduct the world-class science that can only be done in the laboratories once we've returned them. Thank you.
Thank you very much, Charles. I'd like to call Dr. Parker to the podium, who'll tell us a bit about what ESA efforts and their direction. If we could have Dr. Parker's presentation, please.
Good morning, everyone. It's a pleasure to be here, and I think it's great that this panel has been organized today by the IAC, so thank you for that. I want to do three things really today, which is say a little bit about how and why a Mars sample return activity fits into the European Space Agency's thinking about the future of exploration. Update you a little bit on some of the activities that are related to preparing for Mars sample return, and then maybe round it off with some personal views. So the first thing to say is ESA is already involved in Mars exploration. Mars Express has been in orbit around the red planet since 2003. Whilst a relatively modest spacecraft in size terms, it's undoubtedly delivered pretty impressive science across a range of different scientific domains. Right now, we've been working hard for many years now on the ExoMars program, the two-stage exploration of Mars, and we are now only days away from the arrival of the 2016 mission element, the Trace Gas Orbiter and its piggyback Schiaparelli lander. So I'd like to say that the Trace Gas Orbiter, the 2016 mission, is kind of the pocket knife, the Swiss Army penknife of Mars missions. It's a big thing. It's one of probably the largest thing to arrive at Mars since the 1970s. In the sense, it has multi-functions. It's going to provide telecommunications relay functions supporting landed assets in the future and from the get-go. It's also going to do very important science itself, and the key science for this mission is in the orbiter. It's focused on understanding more about the trace gases that were originally identified by Mars Express and some terrestrial observations. So it's going to have some very impressive scientific spectroscopic capabilities and also an impressive stereo imager. So that's the second element. And then the third element is to develop the European capability to land on Mars through the entry, descent, and landing demonstrator. So separation is on the 16th of October. Sometime in late afternoon European time, on the 19th of October, we should have the arrival of Schiaparelli onto the surface of Mars, and then almost simultaneously the orbit insertion of the Trace Gas Orbiter. Now, it's important, again, to emphasize that ExoMars is a great example of a mission that is doing science and technology simultaneously. It's what makes it an exploration mission. And likewise, the next step, the 2020 mission, is intended to provide tremendous scientific return by being the first mission to really explore the surface of Mars in 3 dimensions, not only to rove over the surface, but also to dig below for the first time, to get below, we hope, the surface layers that would have been irreparably affected by radiation over the years. And that is through having this 2-meter drill. The drill has been now built, tested, and works. And it's part of, the drill is a fantastic piece of technology, but its point is to acquire samples and feed them to an analytical laboratory on board the rover, which for the first time will be actually doing astrobiology. So it's an exobiology mission. It's, of course, a key step, and it's a step for us towards the long-term goal of Mars sample return. So take a step back, and as a policy manager now, to say, how does Mars sample return fit into a directorate called Human Spaceflight and Robotic Exploration, or just exploration, if you like. And for me, exploration is much more than science. If exploration without science is just tourism, fine. But exploration is also about the technology innovation. So I always like to say exploration is not only, but also. It's not only science, it's also technology and innovation. It's not only the excitement of going to places, the inspirational value, it's also about international collaboration and cooperation. And that, for me, is why Mars sample return is a beautiful example of a true exploration mission. It brings together the rationale and the benefits of doing exploration. It will have enormous scientific impact. You've heard that already. But I'm also absolutely convinced that the first mission to go to Mars and come back again will excite the public excitement in a way that missions such as Rosetta, which completes its mission early tomorrow morning when it settles onto the surface of the comet, these robotic missions have an enormous inspirational value to the general public as well. So that's why, for a long time now, we've seen Mars sample return as being an important step in our exploration program. So what have we been doing, and what has our involvement been? Well, quite extensive. In fact, studies started as far ago as 15 years in the ESA system. And along the way, we've been developing not only the system studies, not only the PowerPoints, if you like, and being fully involved in the IMAR study activities that started in 2007, but also investing in some pieces of key technology development. That includes work that would support the European Earth return capsule for the samples, design and technology, including miniaturized avionics that would support a sample or fetch rover, another part of the architecture. Quite a significant investment in capture and sealing systems, because one of the challenges is of protecting the samples and protecting us on when the samples come back is developing some really quite complicated mechanisms and clever gizmos that are required to protect those samples, the precious cargo that we're bringing back to Earth. And so that work has included zero-G demonstrations of some of the technology. And so we're looking for an early opportunity to flight test some of that technology on a future Mars orbiter, for example, maybe the next NASA Mars orbiter. And then last but not least on this slide, and for me very important, is to give some serious thought to the eventual sample receiving and curation facility. Having brought these samples back, the challenges of protecting them and using them scientifically over a long period of time, and developing the protocols and the approaches for even transporting them around the world from wherever they land to wherever they are analyzed, is an enormous challenge in itself. This is why Mars sample return is really a system of systems. It's a campaign, and the campaign continues once you come back to Earth. So it will be certainly necessary, in my view, to start investing in the sample curation facility really at the same time as you start to invest in the spacecraft technology. So all of those elements need to come together, and we in Europe have been investing and studying these aspects for quite a considerable period of time now, and we would very much like to continue to do so if our member states retain the support for this kind of work going forward. But turning a little bit to the most recent study activities, recognizing, as Charles has said, the developing architectures that have been put together through the IMARS work, we've been focusing particularly most recently on some studies on the Mars sample return carrier. So how would we, as part of this pass-the-parcel game of Mars sample return, go to Mars but also come back with the samples that have been lifted off the surface, acquired by a fetch rover, that have previously been acquired by an earlier generation, so they're part of the parcel that actually involves coming back to planet Earth. And so we've evaluated configurations for both chemical propulsion and solar electric propulsion. We've particularly been looking at the potential of reusing the electric propulsion technology that is now nearly finished and is going to be used for ESA's science program for the Bepi-Colombo mission to Mercury. And so the trade-offs are really quite interesting in the possibility of having this carrier vehicle launched on the next generation of ESA launch vehicle, Ariane 6, and which version of Ariane 6, and the options and flexibilities between using chemical propulsion on the one side and electric propulsion on the other, trading mass, trading duration of cruise, and so on. Well, all of those really confirm what Charles was saying earlier, that this particular element looks feasible and not ridiculously expensive. It's not a Battleship Galactica mission, it's perfectly feasible. Now, you also see on this slide a reference to Phobos sample return, and in parallel to the work of thinking about Mars sample return, from the European side, we recognize why is Mars sample return important to us? Because to be part of the first mission to go there and come back from Mars is adding to the toolkit of European capabilities in exploration. It's clearly, for me, a precursor to human exploration of Mars, but also there are many planetary destinations where going there and coming back is of interest. But we also have always recognized that Mars sample return is not a mission we're ever going to be able to do on our own in Europe. And if we are to recognizing the successes of Rosetta on the one side, but on the other hand, we haven't gone to an asteroid in Europe, we haven't gone to the moon and come back. Another exciting destination for demonstrating technology, but also doing really important science, are the moons of Mars. And so Phobos is also a destination of interest. And so a little bit of, in a sense, of a programmatic backup. We've been studying and gone through industrial phase A studies with 2 consortia in Europe to define a Phobos sample return mission. And again, that mission is potentially perfectly doable at the European level as a standalone European mission, but is also a possibility that we could contribute to anybody else's Phobos sample return mission. So it's a challenge. There's so many exciting places to go to. Do you want to go to asteroids? Do you want to go to the moon? Do you want to go to Phobos? In our exploration program in Europe, we see all of this as part of a continuous journey. And I wanted to come back with some sort of personal thoughts that we're coming up now for the 10th anniversary of the setting up of the International Space Exploration Coordination Group. And its original product that it put out was the Global Exploration Framework document. I strongly recommend you go away and look at that because it still has fully relevant today. It talks about the interaction between human and robotic exploration. It talks about the importance of all of these destinations, low Earth orbit, Moon and Mars, and other places like cislunar space. But in that, you will see Mars sample return identified already as an international goal. Now, I was just reflecting, sitting there a bit earlier, that I've spent, one way or another, I've been involved in thinking about Mars sample return for more than half of my professional career. And that's a bit depressing in some ways. It's a bit like, when is fusion energy going to arrive? It's always about 15 years in the future. But I think the message, out of all of the recent architecture studies, all of the technology work, is we're getting to the point now where we really should get on and do this. So my personal view is, let's do it. Thanks.
Thank you, Dr. Parker. Next presentation, please. Introducing Dr. Fujimoto from JAXA.
Okay, I'd like to introduce our plan to return samples from Phobos. The planned launch year is early 2020s.
So what this mission will do, I'm not sure if it's... Well, anyway, I can...
Next presentation, please.
What this mission will do is to become a pseudo-orbiter around Phobos, make detailed inspection of the object, and select the landing site, select the sampling site, and land on the surface for a few hours, and do the sampling, and then return back to Earth.
During the return cruise, we will also make a detailed inspection of the other moon, Deimos. So what does this mission has to do with the future Mars exploration? I think there are three key elements. First, it is the first mission to get captured by the gravity of Mars and then come back to the Earth. So this will be the first return trip to Mars system at least. This mission will also make a detailed inspection of the moon Phobos, which may become a key element in the future human exploration of Mars. And the last but not the least one is science, of course. I think everybody knows about the concept of habitable zone. But what's not really well known is the concept of snowline and the fact that all the planets in the habitable zone were born inside the snowline. If you're residing inside the snowline, H2O, the water, is in the form of vapor, which means that when you form a planet, it's really difficult to include water inside the body. So all the planets inside the snowline must have been dry, including those planets now sitting in the habitable zone. So all the planets in the habitable zone cannot be habitable if you don't bring water from outside the snowline. So there must have been a transport process, there must have been a water delivery from outside the snowline to inside the snowline to enable the habitability of the solar system. Who were doing the delivery? We think it must have been the small objects, and Phobos could have been one of them. So the science purpose of this mission is to understand the origin of Phobos. But trying to understand the origin of Phobos is trying to address the question of water delivery in the early history of the solar system. As I said, we plan to launch this mission in early 2020s. We are really happy to collect a lot of international interest from our international partners. And we really hope that to make this mission in best shape through the international partnership. And that's all I have to say today. Thank you very much.
Thank you very much. All right, panelists, thank you very much for those presentations. We'll have a few questions. For Jonathan and Dr. Fujimoto, what will samples tell us locally or globally as they apply to future human exploration? How will it help us further that exploration?
Well, I'll give two answers. One is in areas where humans might, in fact, land and explore, we would want to know what materials are present, particularly what materials that might be hazardous in nature. We also, from a scientific context, want to understand the ages of those sites, and so the type of exploration that humans might do in those regions would depend upon whether they're landing in a place of very ancient crust or an area that's been reworked with water and so forth. And then as well, we would want to understand the biological potential of any samples, and those might be places where astronauts would not be sent to explore because they might then be special regions.
Masaki, your thoughts?
Okay, let me try to give you an answer from different perspective. We scientists, once we know something, we always ask better questions all the time. So if we have samples through robotic missions, we will get more interesting questions, which will be more demanding for human exploration, of course. So once we obtain samples through robotic exploration, I think we will ask the astronauts, whoever he or she is, to be an expert in geology. So, which may not be true all the time, but into the future, maybe we should develop a handy analyzing system or whatever that will assist the astronauts so that he or she can be the expert at the sampling site, and she will collect the truly variable samples back to Earth through the human exploration program. So that's how I see the connection between the robotic exploration and human exploration in terms of returning samples.
Great, thank you. The next question comes from the audience, and the topic is planetary protection. Given that the rovers are not fully sterilized, how will we know that the samples have not been contaminated by Earth microbes? What precautions are being taken? Charles, could you give us some thoughts?
Thank you. Although the rovers as a whole are not being sterilized, the parts of the rovers that we're using for collecting samples on 2020, if those are the ones to be returned, we're getting much smarter about what parts do need to be sterilized and what parts do need to be assembled under aseptic conditions. Our colleagues at ESA on the ExoMars mission have been trailblazers in that area. We're following suit in a lot of those areas. And so even though the vehicle as a whole may not be all of the sampling hardware that will go into direct contact, we're paying a lot of attention to that, paying a lot of attention to how those are sealed up, and also putting in place a series of blanks or witness plates that will go along the way too, so that if there is contamination, at least you understand the source of the contamination when that was introduced along the way. Not a scientist, but the ones that I have spoken with understand that, there's also protocols of looking at what's on the surface of the samples versus what might be inside the samples and ways of dealing with potential contamination along the way that way. So I think we've got a pretty good handle on the concerns about the round trip contamination. The area that we're also particularly sensitive to is the back contamination of making sure that the samples stay sealed until they're back into the Earth laboratories.
All right, great, thank you. On the next question, Elon Musk unveiled his plans for Mars here on Tuesday. I'd like to understand your opinion of how that may contribute to various space agencies' plans for going to Mars and Mars sample return. Dr. Parker, any thoughts on that?
Well, I suppose the answer is that if all of those ambitions start to happen, there obviously creates enormous scientific possibilities to accelerate the process of Mars exploration. But equally, because of the issues around doing the right science and doing the good science that we want to do, we would certainly want to think about what are the protected regions and what's the need to prevent the tourists bouncing around in the most interesting scientific locations. But certainly Mars exploration, and particularly when you think about human Mars exploration, is critically dependent on the transport capability. So anything that accelerates and increases the transport capability is going to contribute to the goals that we want to do with Mars exploration. I think we perhaps at the agency level are necessarily constrained by the realities of funding and proceeding along the routes that we have today. But I think the inspiration and the interaction between the entrepreneurs and the traditional agencies is something to be welcomed, and so very keen on it.
All right, thank you. This question for all of you. What is, in your opinion, what is the most challenging problem confronting Mars sample return?
I was going to say funding, but it's not funding in and of itself. It's convincing the policymakers and the decision makers that we understand what the funding needed is, and that there are viable ways of breaking this into bite-sized pieces, assigning individual technical challenges to different organizations and coming together as a team so that we can get over the programmatic hurdles more so than the technical ones.
Yeah, I think it's a good comment, but I think it's exactly this question of getting the international elements all lined up at the same time. But I think if we don't do it, it's a poor reflection on the capability of space agencies to persuade our funding authorities that the scientific value is so strong. It's so much of an order of magnitude better than anything you can do on the surface of Mars. We have to bring these samples back. They will be a gift that carry on giving. They will benefit researchers generations into the future. But I think actually I come back to the point about the surface facilities, actually thinking about the surface handling, the protocols, the curation. I think that's probably the biggest challenge. I believe the space engineers can do their bit. What we're going to do with the samples when we bring them back is a big challenge for me.
Masaki?
Okay. Well, let me answer this from a scientific point of view. In my view, it's going to be choosing the site and choosing the samples. So the Mars sample return mission that is currently being planned, that is the one that was recommended by, among others, the U.S. Decadal Survey of Solar System Exploration by the National Academy of Sciences, will bring back something like a half a kilogram or a third a kilogram worth of material, kind of spread among 30 samples or so. And remember that the Apollo program brought back samples from 6 sites, and it was hundreds of pounds of moon rock. So Mars is a more diverse body than the moon with a more complex geologic history. And yet, at least for that first sample return, it's going to be a lot less samples. So, choosing the site, choosing the samples to bring back is going to be an incredibly difficult, not undoable, but very, very difficult scientific exercise. And there's going to be a lot of discussion and angst and so forth in trying to decide just what to bring back in that half a kilogram, third of a kilogram of sample.
Thank you.
No one says we have to stop after just one.
Fujimoto, challenges of sample return.
Yes, I fully agree with Jonathan. And the other issue is that, when we explain to our decision makers about our forward sample return, the question we always get is, why do you have to have samples back? Why cannot you do it by individual measurements? Well, of course, it's always better to have samples back, but at the same time, we shouldn't stop developing our technology to do a better individual measurements. I think this is linked to what I said for the human exploration part as well. But well, sample is always nice to have, but at the same time, we should do the best we can do with the individual measurement, and by doing both, I think we can persuade our decision makers.
Sometimes I show a picture of a synchrotron facility on the ground to show this is the kind of facility we need to have to put the samples into. We're not going to take that to Mars.
That's great. Thank you. So we've seen a snapshot of some of the studies of some of the architectures that are involved where we would have humans in the loop for assisted Mars sample return. What are some of the advantages and challenges of these approaches?
Well, I think the possibilities are twofold. There's if humans go directly on the surface of Mars, then we have the challenge of ensuring we land in the locations that are a reasonable distance away from the sites of really high scientific interest. So there's still the challenge of going to Mars and then immediately being able to traverse to somewhere interesting. But then there's also the interesting possibility of maybe we've gone to Phobos scientifically, but maybe Phobos is the stopping off ground for the humans to then control some robots on the surface of Mars as an intermediate step. And it's a kind of option that we've been looking at for exploration in general in Europe. So we did an experiment this spring with one of our astronauts aboard the space station, controlling a rover on the surface of the Earth, going into an unknown location. The astronaut it was a simulated cave, going in there, challenged to find particular samples within a darkened environment, coming back out again. So that kind of collaboration between humans and robots could be a key part of it.
Charles?
In terms of the challenges, I spent a lot of my time in the talk talking about the advantages of cooperative approaches and having multiple parties involved. I would be remiss not to point out there is a limit to that in terms of having multiple different enterprises and multiple agencies involved, as Dr. Parker alluded to. Getting everybody's schedules lined up and getting the programmatic commitments from different organizations and different sub-factions of the organizations can be a challenge. So I think one of the things about, we've had challenges even within NASA of coordinating our robotic program and human exploration program. So the timing of those commitments and making sure everybody can get their pieces together on the same schedule, I think would be one of the challenges of having the human crew directly involved in that. So we have to have some programmatic flexibility in everybody's schedules on both sides, on the human side and the robotic side.
Thank you. I'd like to talk about the importance and the openness of sharing the scientific knowledge that is gained and ultimately sharing the sample, parts of the sample globally, and the importance to do that if we have a global pursuit to the ends of the long horizon goal of getting human presence on Mars. Jonathan?
Well, from a scientific point of view, science is and always has been an international endeavor, and the more scientists from the more countries that have access to these samples, the more not only techniques that can be applied, but the more insights that we'll get from those. And so, absolutely, from my point of view, this has to be an international endeavor, and those samples have to be accessible to qualified scientists from anywhere in the world.
Thank you. Masaki?
Well, we will share our Phobos samples with our international partners, of course. But maybe it's not only samples, but it's maybe sharing the opportunities as well. Like, as I said, I'm sorry to be really have a concrete item on this issue, but like we're planning a mission to bring samples back from Phobos, and in that mission scenario, we will land on the surface for like a few hours. So there is an opportunity for surface experiment. And I hope not only the samples, but I hope we can provide those kind of opportunities to our international partners as well.
Thank you.
If I could just add, Jonathan mentioned earlier that the Mars 2020 mission, which is collecting a set of samples we think would be appropriate to bring back, is bring back on the order of a half a kilo, 30 samples or so, with about 15 grams of each. I point out that the 30 is probably the more operative number, that you're going to be able to sample 30 different distinct rocks, different geological contexts within one area. But the 15-gram number, in fact, is actually based on a lot of recommendations from the science community. They went through the measurements, including the synchrotron, of how much sample is actually needed to conduct the high priority suite. They actually came up with a number that was closer to 7 or 8 grams, that if you get the right rock, the amount of material that's actually needed is not that high. So we've doubled that. In effect, half of the sample is reserved for future measurements that we can't even imagine how we would do today. So the half a kilo may not sound a lot. 30 different rocks is probably the better way to think about it. And do keep in mind that there's a lot reserved for future science, for international distribution, for experiments that nobody's even thought of yet.
Great. Thank you very much. I'd like to close with the following question and get all of your opinion. We've seen in recent history that there are many new entrants into Mars research and development. We have Israel now has an orbiter around Mars. We have the United Arab Emirates that soon will launch their HOPE mission. China. What can be done to allow new entrants to come and contribute and engage in the future Mars sample return architecture? Make their contribution.
I'd say, I suppose, from the policymakers' perspective. So the first thing is to say the fact there are new entrants is fantastic. And so we absolutely want to find an effective way of engaging them. And I think the sense, I made the point before about MSR is always 15 years in the future. It isn't now. We're starting to make the first steps in this campaign. So I think raising awareness of the reality of that at a certain point and engaging through ISEG perhaps a focused effort on how Israel, how the UAE, whoever else wants to get involved in this exercise is probably something we need to do pretty soon now to really give the sense that we're on the way.
I'd just add, we've tried within NASA to approach Mars with a program approach of looking at interconnected missions, interdependent missions. Well, we make a big deal about the amplification factor that the surface missions get from the orbital relay assets. We're excited about TGO's arrival, not only for the great science they're going to do on their own, but joining the fleet of relay assets that are available to support things on the ground. Clearly, there's a lower barrier to entry for orbital missions than for surface missions, and some of the new players to start to become part of a multilateral program and help support roles like future landing site selection or these relay operations. Those are the easy things to do. I mentioned before when I was talking about taking MSR and breaking it up into bite-sized pieces. Hopefully that kind of framework would also provide opportunities for some of the people that are new to the Mars community to come in and make substantive contributions in that front. We'd welcome that.
I'll let Masaki have the last word. How's that?
Okay.
So I'll go next. From the scientific point of view, there are not only the individual national academies of the various countries that get together and interact on questions of scientific cooperation, but most importantly, COSPAR, the Committee on Space Research, is an entity that for over 50 years, maybe 60 years now, has helped to coordinate scientific cooperation among and between different countries. And I would expect that COSPAR will play a big role in the future exploration of Mars and the scientific coordination of that as we begin to ramp up, and we see many more countries ramping up their Mars exploration programs. I think from that point of view, the future is extraordinarily bright and very exciting for having the whole world explore this incredibly interesting place next door to us in the solar system.
Thank you. Masaki?
Well, first of all, we ourselves are newcomers to this business, and then, so in that sense, my advice, our advice will be that maybe do something different. Make some angle to what's been done on the mainstream. That can be a good entry model for a newcomer, like we do. And then the other thing we are kind of learning is that there is a good chance to do something nice through small elements. Small elements added to the main big mission can really do a good job, and that's getting to be a trend in the space exploration business. So I think that's where the big chances are, yeah.
Well, thank you. I want to thank all of you for your time and your contributions in making this plenary hopefully a success, and the audience. And in closing, I think we've had some wonderful discussions on some very difficult topics as we go forward. I can't stress enough how important it is for both the human and the robotic communities to work collaboratively as we look to do more complex exploration throughout the solar system. And with that, thank you all very much for coming.
Your eyes in the morning sun, I feel you touch me in